We move on now to special functions in classical physics. In the last video, we saw special functions in quantum mechanics. So, special functions in classical physics is the focus here now. And in the introduction, we see that special functions arise naturally when solving differential equations governing physical phenomena. They appear when partial fraction differential equations are solved by separation of variables, first of all. Then they appear when boundary conditions restrict the allowed solutions, and they also appear when the resulting ordinary differential equations become eigenvalue problems. And common special functions include Fourier series, Bessel functions, Legendre polynomials, Hermite polynomials, Laguerre polynomials, spherical harmonics, Airy functions, and error function. These functions are fundamental in heat transfer, wave motion, electromagnetism, fluid mechanics, and diffusion theory. Now, of course, there's a video explaining each of these special functions in some depth already. So let's looking at heat equation, we are looking at special functions in classical physics. So one thing we encounter in classical physics is the idea of heat, and we have the heat equation, which is a partial differential equation. The physical meaning of the heat equation is this, that the heat equation describes the evolution of temperature in a material, meaning you have a material, say you have a rod or whatever you want to have, that you have a rod. So the heat equation talks about how maybe if you start heating it from a maybe you have some fire light source here. So if you start heating it, so you have heat concentrating around here, and over time it spreads to other parts of the rod, something like that. So that's the kind of thing heat equation deals with. Or if you heat it from an end, where you're heating from determines how the evolution is going to look like. So the heat equation describes the evolution of temperature in a material, and the general heat equation is partial U partial T. So it's a function of both time and space and time, right? So as you're applying the heat over time, the heat spreads across the geometry of whatever you are heating. So partial U partial T equals alpha del U squared del squared U, right? Where U of x of t is the temperature. So it means temperature is this function of space and time, x being space and t being time. Then you have at alpha, which is thermal diffusivity. That is some measure talking about how well heat spreads in the medium, whether it is wood, metal, or anything like that. So, and that should vary for different kind of materials. Then you have del squared, which is the Laplacian operator. So for a one dimensional rod, right, partial u partial t will just be alpha d squared u dx squared. That's what this is about. So, but if it is two dimensional, it will now be alpha into partial squared u partial x squared plus partial squared u partial squared u partial y squared and all of that. So, and that is subject to these two boundary conditions: u of 0 comma t is 0 and u of l comma t is 0. This tells you that the heat at both ends is 0. So here when x is 0, that is where the heat is being applied. The heat at that point is 0. Then at the other end of the rod, so in this case it's looking like in the case of the rod this usually describes, you might be having something like this kind of rod, and then you apply heat at this point. So you apply heat to this point. So initially the heat, okay, or maybe, yeah, I think this still works, right? So this is like U of X. I mean, when X is 0 here at time, that's 0. And then U of L comma T. I think this still makes sense. So at the two ends, so if you apply your heat here, so at this end, in the beginning, you have the temperature as 0. Okay, so and then we have an initial condition which is u of x comma 0. So when the length is just when at time 0, right, you just have f of x. You have the geometry there right from the beginning for sure. So in this case now you go ahead and do separation of variables. I think we've done this a couple of times even in other situations like that. So if you assume that u of x comma t is, so you separate into time and space, into space and time. So you have x of x multiplied by t of t. If you substitute into the heat equations, you have xt prime equals alpha x prime prime t, dividing by xt now. That's, so that you can separate t to t and x to x. So you have t prime over alpha t equals x prime prime over x. So because they are equal now, so it means that each of them will be equal to the same quantity minus lambda. So the PDE separates then into two ODs where you now have, for this part now, you have x prime prime equals minus lambda x, so that you can now have x prime prime plus lambda x equals 0. That's for the spatial equation. For the temporal equation, that's talking about time. So you have t prime equals minus lambda alpha t, so that you can have t prime plus alpha lambda t equals 0. So the boundary conditions produce the eigenfunction. So if you apply the boundary conditions, you can now have x sub n of x equals sine n pi x over L. I think I dealt with this a lot under the partial differential equations playlist, talking about heat equation, wave equation, and all of that. And then they have eigenvalues lambda n equals n pi over L all squared. So then the general solution becomes something like this. The complete solution is then u of x comma t equals summation from n equals 1 to infinity b sub n sine n pi x over L e raised to minus alpha into n pi over L all squared t, where b sub n is 2 over L integral from 0 to L f of x sine n pi x over L dx. So the sine functions from a Fourier series, the sine function, right, forms a Fourier series basis. This what you have here. So thus the special functions appearing in the heat equation are Fourier sine functions. So if you need a more detailed solution to all of this instead of what I've just explained, you can check my playlist on partial differential equations and go straight to heat equation to see how that goes. Then we have an example here now that if you suppose that f of x is 100 sine pi x over L, only the first eigenmode is present. Therefore, u of x, so we have 100 now. So u of x comma t is now 100 sine pi x over L e raised to minus alpha pi squared t over L squared. So as time increases, the exponential factor decreases and temperature distribution decays towards 0 for sure. So we can then write a code for this. Um, if you follow all this, so we have when time is 0, you have this blue one here at time equals 0. So you have the temperature up there. Then when at time equals 1, you have this next one. So it's going down with the passage of time because the temperature decays towards 0 ultimately. So at time equals 2, you have the green, and at time equals 5, it's already flat at 0. So it's more like you have a heat diffusing, you know. So then you have wave equation. So the physical meaning for wave equation, the wave equation describes vibrating strings, sound waves, and many other oscillatory systems. So it's more like you have a guitar or any other thing. You have a guitar, you're plucking the strings, or maybe you have two poles. You have two poles. uh I'm not very good at drawing, I'll just try. So you have two poles and maybe there's a string connecting these two poles, maybe a tight string for that matter, so connecting the two poles. So maybe you get to jump on the string. So this is a string now, okay? Or like on a guitar where you have different strings lined up on the guitar bass like that. So as you plug the strings, you have some things happening in the strings like that. So the wave equation describes vibrating string sound waves and many other oscillatory systems. The one-dimensional wave equation is d squared u dt squared equals c squared d squared u dx squared. So where u of x comma t is the displacement. So as you plug the string on the guitar, so you displace it. So that's why it is oscillatory, right? So you displace it, then it goes back to its original position. Then c is the speed of the wave speed, the wave generated in the string. C is the speed of that wave. Then we can of course also solve this by using separation of variables, where you assume that u of x comma t is x comma x t comma t, x of x multiplied by t of t. So the substitution then gives, so if you do the same thing like we did before, you get x t prime prime. I also solved this comprehensively under the partial differential equations playlist. So just look for wave equation. It's completely solved. So you have x t prime prime equals c squared x prime prime t. Then dividing by x t, you have t prime prime over t equals c squared x prime prime over x equals minus lambda c squared. So if you put all of that together, you have x prime prime plus lambda x equals 0, because c squared cancels c squared, right? So you just have x prime prime equals minus lambda x. So that becomes this in the spatial equation. For the temporal equation, you have t prime prime over t equals minus lambda c squared. So that's t prime prime equals minus lambda c squared t, which then becomes t prime prime plus lambda c squared t equals 0. So the spatial eigenfunctions are then x sub n equals sine n pi x over L with the frequencies omega sub n equals n pi c over L. So it bears a bit of a resemblance with the idea of eigenvalues we talked about in the talking about the heat equation. So we then have the general solution. So the complete solution is u of x comma t equals summation from n equals 1 to infinity for a n cos the omega sub n t plus bn sine omega sub n t sine n pi x over L. So at the end of the day, right, this is the spatial part, that's x of x, and this, oh sorry, this is the time part containing time t, and this is the spatial part containing the spatial part x, like that. So these are closed normal modes, and each mode oscillates independently. So you see cos, sine like that. So it's all about oscillation every step of the way. And then we talk about an example, a specific situation where the initial displacement, like maybe you pluck a guitar string, and so that means at that initial time, the displacement is a sine pi x over L, where a here is like what you call the what's that thing called now? Yeah, is it it's the biggest displacement, right? If this would go to zero or something like that. So they have there's something that's called, which I've forgotten now. So initial velocity then, yeah, amplitude, yeah, amplitude. So initial velocity then is the udt of x comma 0, which is equal to 0, and then the solution becomes u of x comma t equals a sine pi x over L cos pi ct over L. That's what u becomes for this specific situation, for this specific situation now. So this represents standing wave motion. So for standing wave, right, it feels like you generate one side of the wave and you generate the other side, and then one cancels the other one out, something, that kind of idea. This represents standing wave motion like we see here. So at time t equals 0, you have the blue. T equals 0.25, you have orange. T equals 0.5, you have 0. And t equals 0.75, you have this. So it's like you have movements across this zero part. So we then go ahead to talk about Bessel functions and circular membranes. So for circular geometries, the wave equation, so we are still talking about wave equation, but in the circular domain now, we have del squared u equals 1 over r ddr into r du dr plus 1 over r squared du squared d theta squared. And separation leads to Bessel equation. Bessel's equation, like r squared r prime plus r prime plus k squared r squared minus n squared r equals 0, whose solutions are then j sub n of kr, called Bessel functions of the first kind. And that can be seen, of course, we've seen Bessel itself, so that can be seen in this case. So for j sub 0 of x, we have the blue one, and then for j sub 1 of x, you have the orange one, and the green one is for j sub 2 of x, even as we, I go over all these 0, 1, 2 like this. So we have that. And then we can talk about electromagnetic waves now. So for Maxwell's equations, we're talking about special functions in classical physics. So Maxwell equations are very useful equations when you talk about electromagnetic waves. So in free space, we see that del dot E is 0, del dot B is also 0, such that del cross E is now minus dB dt, and del cross B is mu naught epsilon naught del partial E partial T. Combining Maxwell's equations then gives del squared E equals mu naught epsilon naught partial squared E partial T squared, which is a wave equation. And then that leads us to talk about cylindrical waveguides. So for cylindrical waveguides, the radial equation becomes r squared r small r squared big R prime plus small r big R prime plus k squared r small r squared minus m squared, all multiplied by big R equals 0. This is again Bessel's equation like this. So the solutions are j sub m of kr, and you also have so kr coming from this square root of k squared r squared here. Then you have boundary conditions requiring j sub m of k j of k multiplied by big R, which is equal to 0. So the zeros of Bessel functions determine the allowed frequencies. Then we have fluid mechanics. So for potential flow, for incompressible and irrotational flow, partial squared u del squared phi is 0 for incompressible and irrotational flow. Then this is Laplacian's equation right here. So using spherical coordinates, now we know we have phi of r comma theta comma, yeah, this is phi too, right? Which is equal to r big R of small r, big theta of small theta, big phi of small phi, like that. This, okay, I think this is phi and this is psi. Yeah, big psi of small psi. If I got that right. So the angular equation becomes d mu into 1 minus mu squared multiplied by dp d mu plus L into L plus 1 P equals 0, whose equations are Legendre polynomials. So in this case, now for potential flow, you are talking about Legendre polynomials. So for Legendre polynomials, the first few Legendre polynomials are P naught of x equals 1. So if you want to see Legendre polynomials, I have a video on it already in this playlist. So just want to check that out. So it's fully dedicated to Legendre polynomials. Then P1 of x is x, P2 of x is 1 over 2, 3x squared minus 1. Then P sub 3 of x is 1 over 2, 5x cubed minus 3x. So there you see the so for different ways of generating these kind of equations, things like the Rodrigues formula and all of that. So these functions occur naturally in potential theory, gravitation, fluid flow, and electromagnetism. So you have all of so when it comes to fluid flow and electromagnetism, you see Legendre polynomials coming up there. And of course, if we do this now for range 4, that's from 0 to 3. So for Legendre polynomial for 0, for that 0, this is the blue one here. For at order 1, you have the straight line here. At order 2, you have the green line, which is like a catenary. I think that's what it's called. And then P3, you have this concave and convex, this curve having both concave and convex parts, like that. Then we go on to talk about diffusion problems. The diffusion equation, dc dt equals d del squared c, where c is concentration and d is diffusion coefficient. Mathematically, this equation is identical to the heat equation. Then we talk about a point source. Just like heat too. If you apply heat at a point, the heat moves over to other parts. So it's the diffusion technically, right? So talking about point source diffusion, then if you consider that c of x comma 0 is m delta of x, the solution c of x comma t is equal to m over square root of 4 pi big D multiplied by t exponential minus x squared over 4 dt. This Gaussian profile spreads with time. So, and we talk about error function coming into this now, under diffusion problems. So we have error function showing up here in the sense that for a semi-infinite medium, c of 0 comma t is equal to c sub 0. So this solution becomes c of x comma t, which is equal to c sub 0. The complement of the error function for x over 2 square root of d big T d times t, where the error function of x itself, ERFC is the complement of the proper error function. That's like 1 minus error function. So an error function of x is 2 over square root of pi integral from 0 to x e raised by minus t squared dt. And the error function of c the complement of error function uh, at x is 1 minus error function of x. Oh, that's just I explained up there. So the error function appears because the integral e raised by minus x squared dx cannot be expressed using elementary functions. So this is what leads to this is the Gaussian integral, as it were, and it also has something to do with the normal distribution idea in probability. So we can, do something like this here. So looking at the diffusion profile using the complement of the error function. So you just see that going down like that. Then in summary, we see that we have different physical problems and the associated differential equation and the special function that leads to. So for heat conduction, we have the heat equation. The special function involved is Fourier series. For vibrating string, which is some kind of wave equation, and Fourier series is what we see there. For a circular drum, we have wave equation, and it ends up with Bessel equation. For cylindrical waveguide, we have the Helmholtz equation. The special function attached is Bessel functions. Then for potential flow, you have Laplace equation, the one we just saw, and the special function is Legendre polynomials. Then you have antenna radiation, still Helmholtz equation, with special function being Legendre polynomials. For diffusion, which we just saw, we have the diffusion equation and the special function attached to the error function, and of course the complement of the error function. Then you have the spherical waves, Helmholtz equation still, spherical Bessel functions are the special functions attached in that situation, and you have the multiple expansion, which with the differential equation being Laplace equation and the special function being the spherical harmonics. So you want to check up the video fully dedicated to spherical harmonics, so you can understand the whole multipole thing. So the key idea we see in all of this is that the appearance of special functions is determined by one, geometry of the physical system, the boundary conditions, the separation of variables, Sturm-Liouville eigenvalue problems. So Cartesian symmetry typically leads to Fourier functions. That's the normal x and y axis we know. Then you have the cylindrical symmetry leading to Bessel functions. Spherical symmetry leads to Legendre polynomials and spherical harmonics. Then, thus, many seemingly different areas of classical physics are unified through the mathematics of special functions. So we come for our practice problems. As usual, we have 20 of them. So here you can see, let me see if I can fit in two at once. Okay, I think we can only see one for now. So you have a rod of length L equals 2 meters satisfies all of that. So let me just keep it moving. Of course, I'll be solving problems 4 and 20. Problems 4 and 20. That's one. This is so here we can see 2 and 4. So I'll be solving for which to determine the Fourier sine coefficient of f of x equals x into L minus x on the interval 0 less than L 0 less than x less than L. That's the first problem I'll be solving. Then you have wave equation now. For wave equation, you have problems 5 and 6 shown now, and then you also have problem 7 and 8 still under wave equation. So moving on, we'll go on to Bessel functions and electromagnetic waves, where you can see questions 9, 10, and 11 right there. And then 12 is still under the same Bessel functions and electromagnetic waves. Okay, having done that, we move on to fluid mechanics and Legendre polynomials. Those are the connections there. So you have the Rodrigues formula for Legendre polynomials there. So you have questions 13, 14, and 15. And then 16 is also part of that to show that p sub n of 1 equals 1 for all non-negative integers n. Then you have diffusion and error functions. So for diffusion and error functions, you have problem 17 and 18 as shown right now. And of course, 19 and 20 are also part of that. So we have that. So I'll be solving question 4 like I've shown, and then question 20, which is to show that the Gaussian solution c of x comma t equals m over square root of 4 pi dt exponential minus x squared over 4 dt conserves total mass by proving that integral of minus infinity to infinity of c x comma t dx is equal to m, basically. So let's see how that plays out. Okay. So problem 4 is the first one. We have problem 4, which says to determine the Fourier sine coefficients, of f of x equals x into L minus x on the interval 0 is less than x is less than L. So that's what we have to do. So just go straight up to deal with that. So first thing, we need to remind ourselves of the Fourier sine expansion. So we seek a representation. We seek a representation of the form f of x equals summation from n equals 1 to infinity b sub n sine n pi of x all over L. So the coefficients, I mean, this Bn for instance now, the coefficients are b sub n equals 2 over L, that's big B sub n, equals 2 over L integral from 0 to L, x into L minus x sine n pi of x all over L dx. That is Bn right there. So if we expand that, expanding, we have b sub n equals 2 over L into So that's b sub n equals 2 over L into L integral from 0 to L x sine n pi x over L dx minus integral of x squared sine n pi x over L dx, like that. So if we expand that, that's what we get. Because we split up this now. So we have XL. So we have L out here, and for x squared, you have that remaining here. So that's just the expansion we have going on there. So next, we can so if we let A to be n pi over L. So anyway, you say n pi over L, that is A now. This is A. N pi over L is A. So if we let A be n pi over L, then we have that Bn is equal to 2 over L into L integral from 0 to L x sine ax dx minus integral from 0 to L x squared sine ax dx. So we have that. Don't forget the goal. The goal is to determine the Fourier sine coefficient of f of x equals x into L minus x. So it is more like throwing that into the Fourier thing and getting our result out. So we have this now. So the next thing now, we do the integrals. Okay. So we have two integrals here, as you can see. We have this x sine ax dx, and the second integral is integral from 0 to L of x squared sine ax dx also. So for the first integral, that's 1, this is 2. So we are dealing with this. For the first integral, um, using integration, by parts, we have that integral of x sine ax dx. In case you don't know integration by parts, you can check the playlist on basic calculus. I have that detailedly dealt with there. So you have x cos ax over a plus sine ax over a squared. That's that. And since AL is equal to n pi, because we made this substitution here that A equals n pi over L. So AL is simply n pi, So since AL is equal to n pi, so that means that cos n pi will simply be minus 1 raised to power n, right? So you have that alternating. So when n is 0, for instance, you have 1. When n is 1, you have minus 1. So for even numbers, yeah, it's positive. For odd numbers, it's negative, basically. So in this case now, we obtain this, that the integral from 0 to L of x sine ax dx is equal to minus L into minus 1 raised to power n all over a. So we have this settled for the first integral. So this is the first integral now dealt with. So the second integral, the only difference is in the x squared, right? So we go for the second integral now. So don't forget, this is ax in here, ax. So that's for the first integral, right? So for the second integral, okay, because of the x squared, we also do integration by part, but because of the x squared, we have to do that twice. So if we do that twice, so for the second integral, integrating twice, by parts, we get this result, that integral from 0 to L of x squared sine ax dx will be equal to minus L squared into minus 1 raised to power n all over a plus 2 all over a cube into minus 1 raised to power n minus 1. So you can take the pain of going through that step by step. So minus L squared minus 1 raised by n. But if you want to know everything about partial differential integration by parts, you can also check the playlist on basic calculus like this. So we have that now. So with that in place, that's what we get for the second integral. So at the end of the day, we now substitute everything back. So substituting into the formula for b sub n. That's where we are coming from. So b sub n that we had the two integrals, but don't forget we have a 2 over L here, and then an L to multiply the result we got for the first one, and then the other one we'll just put the result like that. Did I forget to close this up? Yeah, this should be closed up. Okay, so we move on now. Substituting into the formula for b sub n, then we then have b sub n equals 2 over L, the 2 over L that was outside, then into, there's another L with the first integral. So we then have minus L squared minus 1 raised to power n all over A, plus for the second one now, L squared into minus 1 raised to power n over A minus 2 over A raised to power 3 into minus 1 raised to power n minus 1, all of that, to substitute into the formula for b sub n. So we have this, that's b sub n there. So the first two terms cancel. So of course, the first two terms cancel. As we can see, this and this are the same with different signs, so they cancel out, so that we then have b sub n to be equal to your 2 over L multiplied by the rest. So that'll be minus 2 times 2 is 4. Then L times A3, that is L A raised to power 3, right? Into minus 1 raised to power n minus 1, like that. So, and then since A is equal to n pi over L, like we had before, then that means that A raised to power 3 would have to be n cube pi cube all over L cube. So in that situation, then it's we can say therefore b sub n is equal to minus 4 L squared over n cube pi cube. That's simply substituting this here. So we have minus 4 L squared over n cube pi cube into minus 1 raised to power n minus 1, like that. And that is what we have for that part, but we have to do one more step. So we now simplify. So simplifying. So we start for even n, that's when n is even, like I said before, right? We have this part here. So for even n, we have minus 1 raised to power n minus 1 to be always 0. So when n is even, we always have this one to be 1. So 1 minus 1 will be 0. So settled. So in that, hence, it means that b sub n will be 0 in that regard. On the other hand, for odd n, we have minus 1 raised to power n minus 1 will always be. So for odd n, this will always be minus 1. So minus 1 will be minus 2, so that b sub n is equal to 8L squared all over n cube pi cube. Okay, so that's for odd values now. And then we can have a final answer. You can say finally, x into L minus x can then be said to be 8L squared all over n cube. Okay, well, the n can go inside. 8L squared all over pi cube will now be summation from n equals 1, where n is odd, to infinity, for 1 over n cube. So this n cube here goes inside 1 over n cube sine n pi x over L. So that's the final answer That's for that problem 4. Okay, so let's move on to problem 20. So problem 20 now. Problem 20. So for problem 20, we have that. Okay, this is the final answer again, in case I was too fast to move away from that. This is the final answer for, Fourier for x into L minus x. So for problem 20, finally, we then have this. Want to show that the Gaussian Gaussian diffusion solution C of x comma t is equal to m all over square root of 4 pi dt exponent minus x squared all over 4 dt conserves total mass by proving integral from minus infinity to infinity for c x comma t dx equals m, like this. So we go on with the solutions. So first thing, we write the total mass. So we know that the total mass from our study so far, from even in this lesson, I explained that the total mass is actually this m, which is equal to integral from minus infinity to infinity c of x comma t dx. That's the total mass formula. So substituting the diffusion solution. So we then have m to be integral from minus infinity to infinity. Then, so this is the diffusion solution which we already have in the problem, right? So that is m over square root of 4 pi dt exponent minus x squared all over 4 dt dx. So, this c of t that we have, we just fix that up there. So we take constant outside, right? Take all the constant outside because we are integrating with respect to x. So we take the constant outside so that we have m to be m. This special m, now that's why I distinguished it. So this special m all over m square root of 4 pi dt integral from minus infinity to infinity for the exponent of minus x squared all over 4 dt dx. So we have this now, e raised to minus x squared. So that's looking like the Gaussian kind of thing. Okay, so with that in place, then we have to introduce a change of variables. So because this e raised to minus x squared. So just like we would solve the Gaussian integral, we have to introduce a change of variable. So, and to do that, we can say let u be equal to x all over let u be x all over 2 square root of dt. I think the idea for that is this 2 square root of 4 can come out, you have 2, then dt is inside there. So that's probably why this is happening. So like taking the square root of this part so that this can be related with this. So we say let u be x over uh, 2 square root of d multiplied by t. So that means that this implies that x itself will have to be 2 square root of dt under the roots and then u outside, okay? So that dx du or dx, of course, dx du will have to be 2 square root of dt, 2 square root of dt, so that dx can then be 2 square root of dt multiplied by du outside the square root. So substituting then, substituting. So we've fixed this now. For dx, we put 2 square root of dt du. So we put that here, and then we have already made a substitution here. So what that means is that we then have this special m to be big, this m over square root of 4 pi dt integral from minus infinity to infinity, e raised to minus u squared, then 2 square root of dt multiplied by du, like this. So that happens to be another constant which you can push out. So we can simplify the constants. So we know that since square root of this square root of 4 pi dt is the same thing as 2 square root of pi dt. Since we have that, right, we obtain this m now to be equal to m all over 2 square root of pi dt. Then this is a constant now because it's not anything in terms of u. So we can move that out. So we have that multiplied by 2 square root of dt there. Integral from minus infinity to infinity, e raised to minus u squared du, which is the Gaussian thing that we've always been used to. So we have to tidy things up, right? 2 cancels out. Square root of dt cancels square root of dt here, so that m itself now is m over square root of pi, m over square root of pi, integral from minus infinity to infinity, e raised to minus u squared du, which is the Gaussian expression, which we know too well. We know this expression too well. We know that's this part is square root of pi from experience. I think we did that decisively under gamma function or something like that. So we use the Gaussian integral now. So using the this is the Gaussian integral. Using the Gaussian integral, a standard result, a standard result is integral from minus infinity to infinity, which is e raised to minus u squared du, and that is equal to square root of pi. We did that under gamma function. You want to check that it was fully solved there. So substituting, we have this m to be m over root pi times root pi for the whole integral here. Root pi. So root pi just cancels out. Root pi cancels out. Therefore, we have that special m, this special m is equal to the regular m. So in conclusion, right, in all, we can say that the total mass is independent of time, which means that integral from minus infinity to infinity of c of x comma t dx is simply equal to m. And that's what we are expected to prove. If you go to the question, show that the Gaussian diffusion solution, this conserves total mass by proving that, yeah, we have been able to prove this now, that this is equal to this. So it conserves total mass by proving that. So that has been proven. So that we have proven. So the total mass is independent of time, and we have all that. So hence, the Gaussian diffusion, the Gaussian diffusion, the Gaussian diffusion solution conserves mass exactly. It conserves mass exactly, which is one of the most important physical properties of diffusion processes. So we have that. So with this, we come to the end of this interesting video talking about special functions in classical physics. So I'll flash the problems again, and then we'll move on So watch out for the next video. So here we have problem 1, talking about heat equation. Then we have problems 2, 3, and 4 now. Problems 2, 3, and 4. Still on heat equation. Then for wave equation, we have problem 5 and 6 first. And then that's what we have problem 5 and 6. Then we have problem 7 and 8, still on on wave equation, right? Problem 7 and 8. Then we have Bessel functions and electromagnetic waves. That's 9, 10, and 11. Problems 9, 10, 11. Then, of course, 12. Then we have fluid mechanics and Legendre polynomials. That's problems 13, 14, and 15. Problems 13, 14, 15. Then we have 16 also. We have 16 also. Then for diffusion and error functions, we have problem 17 and 18. Then 19 and 20. So let me know how helpful this is for you. And there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. But if you have not subscribed, this is the opportunity. Why not go ahead, subscribe, and of course hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges that you'll find out when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.